Welcome everyone to this engineering course we are offering Introduction to Analog Electronics, a very important topic um, in in automation. Uh, when we talk about signal processing, when we talk about automation, when we talk about how to acquire signals from the real world and bring it to the digital world. So a topic which covers a lot of industrial and consumer industrial segments. Okay, so as before, anyone who has attended our courses before knows this, that we pay heavy emphasis on paying attention to the keywords in this particular title, analog and electronics. Anyone interested in knowing the details, historical details relating to these keywords, highly recommend to click on these links or go to Britannica or any other similar quality source to find out the details about their historical journey. Okay, so let's carry on. So we offer all of these courses under Contact Field Institute, which is an affiliated company with Soft Galaxy Technologies Inc. This is our LinkedIn profile page. Highly encourage if you want to connect with us to visit this page and to find out what we do, what we have done in the past. Or you can connect with us. You can send us an email to info@hsclouds.org. HS stands for Humanity Serving. So this email, or use softgalaxy.hsclouds@gmail.com. So one of the key things what we believe in and we try to emphasize to our students is that there is no shortcut to glory. People talk about it, how you can quickly achieve it, something and be successful. You talk about an individual or a project or whatever it is, there is no shortcut. You have to make sure that you pay attention to the basics and you take the right path in achieving the desired objectives. Okay, let's carry on. So by taking this course, these are the potential career options you can think of. Will give you knowledge relating to um, analog electronics designing or troubleshooting, and also basically you can be an electronics repair technician, relating to if you're only just have taken a course like Introduction to Analog Electronics. So this is the distribution of marks in this course. Like before, anyone who has attended our courses before knows that this particular distribution is pretty standard. Our main focus emphasis is on testing, hands-on um, abilities you acquired during this coursework. And we want to make sure that you not only have clearly understood the concepts, but you also have the required hands-on skills, which will make you eligible for potential job opportunities. So 10% is the assignments, 5% we give it before the midterm, and 5% before the day of the final. Lab work is 20%. So when we talk assignments here, so any labs we will assign to you will be you have to do it at your own time, or if you're attending a facility which has provided you with the required um, environment, the lab work will be included along with the assignments we give during these lectures. So 10% is assignments, which includes the lab work which is assigned to you. Over here, this is the testing of the lab work, 20%, which is a 1 hour exam before your the day of the midterm and before the day of your finals. So 10% will be your exam on lab work on the midterm day, and 10% on the day of the final. So this exam you will do before your written midterm exam. We will give you a half an hour, 1 hour break before you do your midterm on the day of the midterm, or before you do the finals at the day of the finals. Okay, and we will be doing industrial tours, ideally 4, in order to give you the practical knowledge on how uh, this analog electronics is basically you know kind of how industry or consumer applications utilize analog electronics for their respective purposes. Okay, let's carry on. So the objectives of the course is to establish a firm understanding in designing and working with analog electronics circuits and systems, be able to troubleshoot such circuits and systems. That's the course objectives. Uh, so there are some links. You might have, if you have attended our courses before, you might have seen these YouTube videos. But over here, the emphasis is without going into and seeing these videos, once you have the slides, I highly encourage you to look into those videos, because all of these systems employ analog signal processing. Like in the case of cell phone manufacturing, or basically what I'm trying to show you here, that cell phones are basically circuits which employ analog electronics on their PCBs. Similarly, in robotics, there is a heavy use of analog electronics. Same like self-driving cars or Amazon's order fulfillment center. So it's majority of these um, systems use digital technology, but analog electronics is an essential, integral part of these systems. Just to emphasize that this learning is very important in order to bring you or to give you to the knowledge levels required to basically understand overall system architectures. Okay. So these are the required equipment for the lab work. I think you must have seen all of this, what we have done in one of our prior course, Introduction to Electronics, Electrical and Digital Circuits. The main difference here is that rather than working with digital ICs, we will be working with op-amps, and these are some of the op-amps. Um, among these, we will be using it for some of our lab work. Okay. So these are the basic electronic components. You are expected that you are familiar with these components. Like these are capacitors, axial capacitors. This is an SMD capacitor, SMD. These are the resistors you see here, relay, transistors you see here. Again, these are transistors. Some of the op-amp ICs or ICs of different functionalities, diodes, maybe Zeners. So it's expected that you are familiar with these particular components, because you have required knowledge necessary to take this course, because we will be taking this course is about going to the next level of your learning from the basics of these electronic components to the level in dealing with analog electronics, analog circuits. Okay. Yeah, so these are the transistors, because analog circuits use, heavily used transistors. So that's the reason of showing transistors or op amps. Just showing it here. The transistors come in various sizes. This is the power transistors, in different shapes and sizes. When we talk about shapes, we mean packages is another term we use. Okay, so same here. These are all, mostly these are DIP ICs, 8-pin DIP, or SOC is the name of the package. Uh, uh, so, so, so these are just to show you that transistors comes in as an axial component like this, or DIP IC, or they come as a SMD component, and you're familiar with that SMD stands for surface mount device, and DIP is a dual inline package. Okay, when we talk about axial, so I mean the components which has legs, like these ones. So we expect that you are already familiar with these terminologies. Okay, let's carry on. Yeah, so as we have done in the past in our preliminary course, in reading register values, we will also go in detail how to read capacitors or inductors and other electronic components. Basically, we'll just focus on capacitors and inductors, how to read their values if you have one in your hand. So this is a case of axial capacitor. As you can see here, the number is written here, 47. Most of the time when you hold a capacitor and you see a number, that means that corresponds to a picofarad value. So like 47 in this case, no other thing means it's a 47 picofarad value of the capacitor. In some other cases, you have three numbers like this one. The third digit will be 10 to the power, or the number of zeros goes after that digit. So it will be 10 into 10 to the power 4 picofarads. So it's a picofarad and a multiplier. And this explains this. As you can see here, 47 multiplied by how many zeros? This is a wrong, I think, because anything multiplied by 0 is a 0, which this screenshot is trying to show that 10 to the power 2, so it means you're just adding 2 more zeros, so it will be 4700 picofarad, the value of this capacitor. In other cases, you have capacitors with these letters, capacitor values alongside with these letters M, N, or RK, and these basically are the tolerances, the variations of this capacitor value. This is what it stands for, and we will look into and we will learn about this M and K during this particular course. And this is an SMD capacitor, and we will most of the time it's pretty similar to this numbering scheme, that you have numbers written in the top. 2 means the value will be in picofarad, and the third is a multiplier, 10 to the power, and the value of this will be in picofarads. Let's carry on. Yeah, so this is the most basic block diagram trying to show that when we talk about analog circuits, most of the time in industrial and consumer applications, that's how the block diagram look like. First of all, we live in an analog world. So the idea is, in this analog world, what environmental parameters we want to monitor. For example, the most common one is temperature or humidity or pressure. So it means we need a transducer or a sensor which can basically pick up that environmental parameters and convert into an electrical signal. So that's what the job of a transducer is. So it picks up. Assume that it's an environment, like a worldly environment, conventional breathing environment, and or maybe you can think this as something you want to monitor underground, or something you want to monitor on a surface. Irrespective of that, the idea is you want to pick up signal, the environmental signal, and we can do that by using a transducer. Okay? That's the number one step, is to on any when we talk about analog system, is basically the number one step. And this can be a mic, where someone talking in the mic is basically the air vibrations converting into an electrical signal. So once we have that signal acquired, the signal is weak because the transducer, the only job of the transducer or the sensor is basically to perform those tiny variations, vibrations in relation to the signal of interest, and to bring it at the output. So those fluctuations or vibrations, the next step is to amplify it. So that's exactly what we do. We amplify those tiny vibrations to make it kind of in an amplified form, so that we can further process it, and in an analog circuit design case, because when the transducer is picking up the signal of interest, the background noise is always there. So when we amplify the signal, it means the background noise is also getting amplified. So we just want to, since we are in the case of a microphone, or in the case of a temperature or humidity, they are in a certain frequency range. All of those signals I talk about, like temperature has its own frequency range, humidity has its own frequency range. In case of human voice, it has its own frequency range. So what we do, we filter. So we let the desired signal go through while filtering everything else. So everything else other than the signal of interest is a noise for us, and that's what the third step is, that we filter it out. So at the output of this, now we have an amplified signal of interest for further processing. So in this case, now, so this is what we call it as analog signal processing. So after filtering, it can the signal can go into for digital signal processing route. It can take a digital signal processing route. Even if our intention is to process the signal digitally, it can be the case that it can go after filtering, or even after amplification. The route is a viable route, because this filtering option we can implement digitally in a digital signal processing route. So this particular block basically becomes a part of digital signal processing route. Okay, any questions you have, please write down in your notebook for our Q&A sessions. Or after filtering, we can the signal can go on for the analog signal processing route. So it's basically, since this is all analog, so this analog signal processing continues. So in this particular course, we will be focusing on these sections. So it's all about analog, so we will be focusing on only analog side of it. Okay, we will since to go to the digital signal processing route, you need to convert the analog signal analog signal to digital. So we will cover analog to digital conversion in this course, but not beyond that. Beyond that is part of the digital side. So since our focus in this course is only analog, so we will cover analog to digital converters, how they work, and and learn about it. Similar to that, we will cover digital to analog converters as well. Okay, so let's carry on. Yeah, so as mentioned in the previous slide, so since this is also a valid route where a microcontroller, microprocessor, computer, DSP, you name it, or even in FPGA, is throwing out digital data, and the intention is to convert that data using a DAC, which stands for digital to analog conversion, or a converter. So the digital data is getting converted into analog format, and then we amplify and then filter because there will be a noise in the conversion process. So we filter the signal of interest, and then we can either transmit it or do whatever we need to do with that analog signal. In case of, let's say, voice, so this digital data can be a digital voice. We convert into an analog form, remove all the noise in the background using filtering, and then we transmission mean there is a speaker which basically does the which converts electrical energy into vibrations via diaphragm, and those ear fluctuations, vibrations reach our ear, and we hear the amplified voice. Yeah, so in this case, we'll be focusing on this along with DAC as well. Yeah, so this we have covered in the past in our preliminary courses. That what is an AC signal? We talk about it, and what is a DC signal? We're just revising it. That AC signal is an alternating voltage with respect to time. That's why it's called alternating current. DC stands for direct current, and that's as you can see here, it's a direct line. And we already learned that what is a peak voltage, what we mean by a peak voltage. So this will be a peak in this case to the shown on this slide. This is the peak voltage. This is the peak voltage of the DC, and there is also a term we use, which we call it as peak to peak voltage, which is from the negative peak to the positive peak. We call it as a peak to peak voltage. And since it's alternating, as said before, that's why we call it as AC signal with respect to time. And here it's DC because with respect to time, it's stable, not fluctuating. Alongside that, there are some more examples just for bringing clarity to analog signals and what kind of real world analog signals can be. In this case, this is a speech signal. The speech signal in electrical form, looks like this, as you can see here. And in this case, it's a seismic signal, like earthquakes or earth vibrations can be picked up by the respective transducer sensor, and realistically, a seismic signal in an electrical form looks like this. So alongside, as I mentioned before, we'll be working with op-amps 741 or something similar, but we will also discuss instrumentation amplifiers. So this INA 128 or INA 129 are the very popular, well-established instrumentation amplifiers from Texas Instrument, TI for short. So we will be, and the reason behind that is to bring in, kind of quality information in this particular course, that how the amplification job for most of the industrial consumer applications, like the design of a PCB or a prototype, can be further, kind of enhanced in relating to saving time, because as you can see here that majority of there are three op amps, as you can see here, right? So all the complexity relating to desired functionalities of a designer are taken care here. Like the gains is very simple. You just have to take care of this RG resistor, as the G stand here for gain, and you just need to put in the value here in order to achieve the required amplification. For a differential, as you can see, this is a plus input, this is a negative input. So for a differential signal or for a single-ended, in case of single-ended, the only thing that you have to do is to ground the negative side. So you just ground it directly, or depending on your application, or through a resistor, you just ground this input, connect after the sensor or a transistor your signal to the input line, and get the required amplification at the output. And you can also provide a reference, so basically, all the complexities relating to amplification of a sensed signal from the transducer or sensor are taken care in instrumentation amplifier like this. Okay, so you just use one IC, connect your signal, and can get the required amplification. And we will do experimentation, lab work, and learn about these instrumentation amplifier, and especially from Texas Instrument in this particular course. The such ICs come in the SOC packages or DIP packages as well. So here's a block diagram taken from TI website. So as you can see here, on the x-axis is the bandwidth. So this which frequency range you're working on, you pick it. So if your frequency is less than 0.15 megahertz, or if it's greater than 28 megahertz, you can quickly, by looking into this particular chart, you can decide, okay, this is going to work for you in this particular voltage ranges, and this is its current range. Most of the time you're dealing with low frequency signals in real world applications, so this is the most common area or frequency range we work with. So you're looking into these instrumentation amplifiers, and as you can see here, these are the voltage ranges: 1.8 to 5.4, 5.5, or 36 volt, depending on your application. So all the parameters are given in this very nice kind of a chart, and we will discuss these in detail in this particular course. We will also discuss Smith chart. What is a Smith chart? That's exactly how it looks. You can print it. You may find it in books of RF electronics, radio frequency electronics, wireless circuits. So the entire function of a Smith chart is to find or match the impedance. When we talk about impedance, we will discuss, because we talk about resistance in our preliminary courses. Resistance is obviously it's simple the function of a resistor. When we talk about impedance, we mean that whatever the resistance is, it's frequency dependent. So resistor itself is a linear component, it's not frequency dependent. But other components we know that, like capacitor is frequency dependent behavior, and inductor is a frequency dependent component behavior. So it means when we talk about impedance, we are talking about resistance, capacitance, and inductor, or a combination of any of these two in a particular circuit. And why we talk about impedance matching, because we talk about impedance matching because our intention is to transfer the power, the signal, to the fullest from circuit point A to circuit point B. Because if there is impedance mismatch from two circuit sections, the signal will be lost or it will be a return signal. So that is unintended, undesired. So that's why this particular Smith chart will help us match impedances to to achieve desired objectives. So we'll go further in detail during this particular course. We will also cover the guidelines, how to lay out a mixed signal PCB. What mixed signal, you already know PCB stands for printed circuit boards. When we talk about mixed signal, that most of the time it means that that particular PCB has an analog section, as you can see here. This is an analog section and it has a digital section as well. So that's what we mean by a mixed signal. So we will cover the guidelines, how such a PCB should be laid out, what guidelines should be followed in order to achieve the best performance out of your design, because that is a very, very important area where industrial and consumer related printed circuit boards, or the designers require, and that will really help you achieve desired objectives in relating to when you're designing a particular mixed signal PCB. Okay, let's carry on. So these are the three tools we will be using and we'll be learning during this course: the MathWorks, Simulink, Multisim, and LTSpice, and they are all three very popular tools used not only in educational institutes like university colleges worldwide, but they are also the tools utilized in industrial market segments for the required needs. So learning these three tools is a part of Introduction to Analog Electronics. So these are the preliminary course requirements, like a high school or college, decent knowledge of math and physics, and a decent understanding of the basics of electronic components, circuits, and or an attending of this course, which we offer through our contact field institute, like Introduction to Electronics, Electrical and Digital Circuits. Attending this course is not mandatory by any means, but if you know the basics, then you're all good. So these are the list of references we'll be following during this particular course. And again, so thank you very much, and we will connect. Take care.